Okay, so let's start our lecture today. So, let's see. So we have, so we want to show that the, so I think last time I just say in word about why this converges. Okay, so so we literally show that this converges uniformly on K, right? So basically what we want is that we want to show the convergence of the sigma function. Okay, so so that okay, let's see. So 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 then so then so this shows that okay. So I think this K is like an arbitrary set, arbitrary compact set, right? So hold on. So I think there might be some issue here. So so this shows that, let's see. So this shows that okay. So this shows that the function okay. So sigma z, which is equal to so z times the product, because here we start with indexing on this n naught plus 1, right? So let's see j from 1 to n naught. Of 1 minus. So we will just multiply the first head terms back. E to the z over omega j plus 1/2 z over omega j squared times e to the l z is well defined on K. Okay, so what I have in mind is that because I think this n actually because these tail factors, I think they sort of depend on the k, right? So maybe let's say on different k, we will have like a different heads and also different the tails, right? So, but we want to show that it defines like so definitely the convergence. There's no problems about convergence, right? So I'm just wondering. I want to show the local uniform convergence, right? Yeah, so this shows the convergence on K. Okay. Okay, so let's say it's sigma kz. Okay, it's because this is only defined on K. So so let's see. So and then so we can define this by any compact set K, right? So K is compact. Implies that or should not K is compact. So K is arbitrary, right? K is arbitrary implies that so yeah, I want to show that. So basically, I want to show that yeah, so K is arbitrary implies okay, so maybe I think I need some other argument. So basically I want to show that so because I want to basically for 1K, right? So I can find some I can use the local uniform convergence of this log function to define the limit function on the compact subset K, right? So, but this convergence depends on K. So basically, I want to just define the sigma z using like different K's, but what I need is that I think I need some argument to show that for different. So for example, what is the situation where you have like two compact sets that intersect, right? I want to show that even though they intersect, they still define the same function, right? So okay, so let's say that. So So we define. I think even though the K's are like different, but with different K, I think their pointwise limit is the same. Okay, so let's see whether we can define the function in this way. So define sigma z to be equal to so sigma kz for where z is in K. Okay. K compact. Okay. So let's show that. Sigma is well defined. Okay, so I think it's very straightforward to show that sigma is well defined because so okay, so let's see. So that K prime. Okay, so be another be. So let's say that so fix. Let's say z naught in C, and that K comma K prime be compact subset. Yeah. So yeah. So subset of C be compact. And we have the condition that z naught is in the intersection of K and K prime. Okay. So yeah. So our goal is to show that sigma of kz is equal to sigma k prime z, right? Sorry, sigma kz naught is equal to sigma k prime z naught. So so by the construction, okay. By the construction, because by the construction of sigma k, okay. So because for k, right? So we know that there is a head and part, right? So yeah. We have sigma k z naught, which is equal to, let's use this letter again. Okay, so z times the product j from 1 to n naught of 1 minus z naught over omega j times, so this is the head part, z over omega j plus 1/2, oh sorry, this should be z naught, times z naught over omega j squared times e. So, okay, so I think maybe I should give this LZ a name because I want to, yeah, because I want to use a different letter for this LZ later, right? Okay, so because in this case, right? So in the n-naught case, this LZ basically it starts from this n-naught, right? So the limit of this LNZ start with index n-naught plus 1, right? So so let's use the letter L of capital N-naught, upper N-naught, okay. Yeah, so where this LZ of capital N-naught corresponds to this specific LZ that's corresponds to these tail factors, okay. Of these out, okay. Okay, so maybe I think to be clear, okay, so I think I may want to change this one to L n naught z to upper n, okay. Okay, so L n naught z to be the limit n naught goes to to be limit let's say n goes to infinity of L of n naught n z, okay, for z in k, okay. Okay, so okay, so let's see. So now we have so similarly for we have, so we apply the same thing for the sigma k prime at z naught. So let's use z times the product. Let's use n naught prime. Okay, so 1 minus z naught over omega j times e to the z naught over omega j plus 1/2 z naught over omega j e to the L of n naught prime of d naught. Okay, so I think they are the same. Okay, so how do I show these are the same? So so let's see. So so first I want to show that. Okay, so let's see. Okay, so let's say so exercise sigma k prime of z naught is equal to sigma k of z naught. Okay. So so let's say assume without loss of generality that let's say that this n naught is bigger than this n naught prime, right? So so I think the idea is that we can break this L of upper. Okay, so let's use this L n naught prime is bigger than this n naught. Okay, so otherwise we just switch the order. Okay, so so here what we have is that so basically the idea is that we can factor out some part of the logs from this L of n naught. Okay. Yeah. So we have L of n naught prime of z naught. So which is equal to which is equal to so the sum so what do I want? N naught is bigger, so basically wait, so if we start with n naught, right? So if we start with n naught, okay, so I should use the other way. Okay, I should use the other way. So I should start with L of n naught, because L of n naught is the one that starts with the lower number, right? So starting with the lower number and summing up so that it has more terms. And L of n naught prime, it starts with a bigger number so that when it sums up, it has less terms. So we have L of n naught of z naught which is equal to, so first we sum from, because here it starts at z0 plus 1. Shoot. Okay, so this is equal to the sum from, yes, it's a little bit, so j from n0 plus 1 to, let's say, n0 prime, okay, of this guy, log of 1 minus z over omega, sorry, z0 over omega j plus z0 over omega j plus z0 square over omega j plus the sum from n0 prime plus 1, okay, to shoot, okay, so here I should use this letter n0 nz, okay, okay, of course this n needs to be bigger than this n0, bigger than this n0 prime, right? So maybe I will write n bigger than n0 prime, okay. So of the same thing, okay. So so this implies that and then this guy, we know that this is L of n naught prime, n of z naught, right? Yeah, so this is exactly that. And then, so this implies that let's see. So this implies that L of upper n naught, right? So this is the limit of this whole thing, okay, of z naught. So this is equal to the sum j equal to n naught plus 1 of n naught prime of this log plus this plus the limit of the other thing, okay. L of n naught prime, okay, of z naught. Okay. So okay, so and then taking the exponentials, right? So taking the exponentials, so this implies that e to the e to the e to the L of n naught of z naught, okay, so which is equal to e to the sum of this guy, right? J from n naught plus 1 of n naught prime, okay, of this guy, plus L of n naught prime of z naught, right? So, okay, so this is equal to what? So this is equal to, okay, so then we just distribute the sum of the product into the product of the exponentials. So because each of the sum here is exactly the log, right? So this is equal to the product of so and the log cancel out with these exponentials. So we have j from n naught plus 1 of n naught prime. Okay. So of shoot, this is not exactly the log. Okay. So this is okay. So when we take the exponentials of one of them, right? So what we have is that we have e to the log, which is cancel out, and then over omega j, and then however we still have e to the sum term, right? So times e to the z naught over shoot, I'm running out of space. So times e to the z naught over omega j plus okay, so plus okay, so so here is 1/2 times z square over omega, sorry, z naught square over omega j squared. Okay. So this takes care of the sum term here, and then times e to the this guy, right? L of n naught prime of z naught. Okay. Okay. So yeah. So here we can clearly see that so after taking the product, because this whole thing, right? So this is like the expansion of just this term, right? So after plugging in this whole thing into this term, and then this product will combine with this product, and then they just form the product from j from 1 to another prime, right? So plugging in into, let's say that sigma k of z naught. Okay, so this expression, we have the equality. Okay, so we have that so sigma k of z naught, which is equal to sigma k prime at z naught. Okay. Yeah. So this shows the well-definedness of this sigma function. Okay. Okay. So so this is only shows the well-definedness, but I think I still need to check that this is an entire function, right? So so let's check it next time. Okay. So okay, so need to check. So sigma z is entire. Okay. Okay.